Imagine you are standing on a quiet hill, watching the sky turn from deep blue to soft purple, then to glowing orange as the sun edges over the horizon. The air is still, the world feels calm, and that bright disk seems like the safest, most reliable thing in your life. You feel its warmth on your face, and you might think of it as a gentle lamp that has always been there and always will be. Yet the light that reaches you in that peaceful moment started its journey long before any human walked the earth. It crossed space, battled through violent storms of plasma, and clawed its way out of a star that is anything but calm. The real story of that sunrise is far stranger and more dangerous than it looks from your hillside. And once you see it, you cannot unsee it. If we trace that warm glow backwards, we start in the back of your eye, where photons trigger tiny electrical signals. Those signals race along your optic nerve into your brain, where you build a picture of the world. The colours in the sky come from those photons scattering off molecules in the atmosphere, with reds and oranges bending through more air than the midday sun ever does. Before that, those same photons spent 8 minutes racing through the vacuum between Earth and Sun, crossing a gap so large that our entire planet would vanish into a dot. And before that, they had to escape from the sun itself, from the outer layers of a star that looks smooth from here, but up close is a boiling, tangled ocean of fire. From Earth, we are used to the idea of the sun as a neat yellow circle. Children draw it as a friendly disk in the corner of a page, with straight rays shooting out. Even many adults quietly carry that same picture in their heads. In reality, the sun is a sphere of plasma, a state of matter where atoms are ripped apart and charged particles roam freely. Inside that plasma, magnetic fields twist, snap, and reconnect in ways that would tear a solid object to pieces. Gravity squeezes this star inward with unimaginable force, and nuclear fusion in the core pushes outward, holding the whole thing in a fragile balance that has somehow lasted for billions of years. For almost all of human history, we could only guess at what was happening on or inside that blinding disk. You cannot stare at the sun without burning your eyes, and looking at it through a simple telescope is even more dangerous. All we had was the smooth white face and the odd dark sunspot when the atmosphere cooperated. It was easy to imagine that the sun was simple, that it just glowed and did not change much. Even as we learned that stars shine because of nuclear fusion, the visible surface still looked calm compared to the stormy clouds and oceans we see on Earth. That illusion began to break when we learned to look at the sun in more than just visible light. Modern solar observatories, such as the Solar Dynamics Observatory, were launched to stare at our star continuously across a wide range of wavelengths. By tuning their eyes to ultraviolet and extreme ultraviolet light, they reveal structures that our eyes cannot see at all. Each wavelength acts like a different filter, highlighting plasma at different temperatures and heights in the solar atmosphere. When you look at those images for the first time, the sun stops looking like a simple ball and starts to resemble a living organism made of fire. At 1 million Kelvin, well above the visible surface, the outer atmosphere, called the corona, glows in extreme ultraviolet light. In those images, the sun appears as a dark disk, surrounded by a halo of wispy, branching light that stretches far into space. The corona is so hot and so thin that you can only normally see it during a total solar eclipse, when the moon blocks the blinding photosphere. For a few minutes, if the sky is clear and you stand in the narrow shadow path, you can watch a ghostly white crown bloom around the black circle of the moon. It looks almost delicate, like blown glass, but you are looking at plasma with temperatures that make molten rock seem cold. Space telescopes show that this halo is not a smooth glow at all. It is filled with loops, arcs, and streamers of hot plasma that trace the sun's magnetic field lines. Darker regions, called coronal holes, open like ragged patches where magnetic field lines do not loop back to the surface, but instead reach out into the solar system. Along those open paths, charged particles escape more easily as a high-speed solar wind. We do not just admire these features because they are pretty. When those high-speed streams sweep past Earth and collide with our magnetic field, they can trigger dancing auroras in the polar skies and jostle the space around our planet in ways that matter very much to our technology. If you compare images of the sun taken at different ultraviolet wavelengths, the change can be startling. One wavelength might show a fairly quiet corona, with large, smooth arches rising from the surface. Another, sensitive to hotter plasma, suddenly reveals bright knots and active regions crackling with energy. The same place on the sun can look calm or furious depending on which layer and temperature you are watching. What first seems to be a single event, a bright flare or a dark patch, often turns out to be the tip of an intricate chain of processes stacked one above another like the floors of a burning skyscraper. And we still have not yet reached the surface you see from Earth. Between the corona and the deeper layers lies a narrow band known as the transition region. It is only about 100 kilometers thick, a tiny fraction of the solar radius, yet across this shallow distance, the temperature rockets upward from thousands of Kelvin to hundreds of thousands. If you imagine walking from a warm beach to the inside of a blast furnace in a single step, you still have not quite captured how extreme that jump is. This is one of the places where our understanding of the sun begins to strain, because the heating seems to run backwards. Instead of getting cooler as you move away from the hot core, the gas above the surface suddenly gets hotter again. Below that strange thin layer lies the chromosphere, the lower atmosphere of the sun. It is thicker than the transition region, stretching for more than 1,000 kilometers above the visible surface. When you look at images of the chromosphere tuned to special wavelengths, the clean, round disk is gone. In its place, you see a forest of thin, jet-like structures called spicules. Each one is a narrow fountain of plasma shooting upward from the surface at speeds that can reach 100 kilometers per second, roughly a few hundred times faster than sound travels through air on Earth. They sway and flicker like long grass blowing in a restless wind, appearing and disappearing in minutes, covering the sun's face with an ever-shifting thicket. These spicules are not just decorative details. They may be an important way that energy and mass move from the lower atmosphere into the corona. Each jet is guided by magnetic field lines that twist and bend as the convective motions below shuffle them around. When you step back and watch time-lapse videos of the chromosphere, you see a restless, pulsing skin rather than a static surface. The sun breathes through these jets, pumping material up and letting it fall, in a ceaseless exchange between lower and higher layers. Every so often, that rising plasma does not escape into space. Instead, it slows, cools, and condenses into denser clumps suspended high above the surface. Under the pull of gravity, these clumps then fall back down, tracing arcs of glowing light. From a safe distance, we call this coronal rain. It is the sun's version of a storm cloud emptying itself, except that the raindrops are millions of degrees hot and the puddle is a surface of churning plasma. Watching that rain through the eyes of a space telescope feels almost unreal, as if the star has started to imitate the weather patterns of a planet. All of this structure is driven by the movement of plasma underneath the visible surface. The sun's outer layers behave like a pot of thick soup heated from below. Hotter material rises, cools at the surface, and then sinks again. These convective motions create cells called granules on the photosphere, each about the size of a small country. To your eye, through a solar telescope, the photosphere can look mottled, like orange peel or boiling oatmeal. To the sun, these patterns are the scars of endless motion. As that plasma flows, it drags magnetic field lines with it, twisting and stretching them. Over time, the field lines can become tangled and tightly wound. When they snap and reconnect, they release bursts of energy that can heat nearby gas and fling particles outward. These magnetic gymnastics are behind many of the features we see in the corona and chromosphere. Even when the sun looks quiet in visible light, deep down, those fields are always shifting, always reconfiguring, as if the star is tidying up mess after mess it keeps making for itself. From our hill at sunrise, none of this turmoil is obvious. The light feels steady. Days blend into one another. It is tempting to believe that the sun is unchanging and benign, a stable backdrop against which human history plays out. Yet scientists have learned that the same processes that give us soft dawns also power eruptions that can span hundreds of thousands of kilometers and pour out energy on a scale that dwarfs anything on Earth. The sun is not just a light bulb overhead, it is a dynamic engine whose moods ripple through the space around it. When you hear that, it is natural to wonder why we are still here. If the sun is so active, why has it not wiped out our electronics or stripped away our atmosphere already? The answer lies in both luck and distance. Earth's magnetic field and thick air act as shields, absorbing and redirecting much of the charged particle storm that spills out from the sun. At the same time, we now know that there have been moments in history when that shield was tested by enormous solar outbursts, and there will be more to come. A calm sunrise does not mean a calm star. It only means that on that particular morning, you are catching it between storms. The more closely we look at the sun, the more our feelings about it shift. Awe at its beauty mixes with concern about its power. Gratitude for the light that feeds our crops stands alongside a quiet unease about flares and storms that might knock out a power grid or blind a satellite. If you work with technology that depends on satellites or on long power lines, solar images are no longer just pretty pictures. They are weather reports for a wild environment that connects directly to our modern lives. And this is only the surface story. We have traced photons from your eye through the atmosphere and into the layers of the solar atmosphere, and we have barely scratched the outer skin of the star. We have not yet followed them into the depths where fusion actually happens, or into the mazes of the magnetic field where violent storms are born. We have not yet asked how the rhythms of this star might reach all the way down into our climate, our biology, and even our minds. To understand how a tranquil sunrise can emerge from a furnace of plasma and magnetism, we have to keep going inward. To go inward, we first have to change how we see the sun. There is no solid surface to stand on, no hard crust to lean against. What looks like a sharp edge from Earth is really a thin fog of plasma, growing denser and brighter as you move down, then giving way to the churning interior beneath. When you zoom in with the right instruments, that supposed edge stops behaving like a boundary and starts behaving like the skin of a storm. Imagine taking a high-resolution image of the sun and gradually increasing the contrast. At first you see a smooth disk with faint mottling. As you enhance the fine details, a pattern of bright cells and darker lanes appears, like the top of a pot of porridge just starting to boil. Those cells are granules, the tops of convective plumes where hot plasma rises, radiates energy into space, then cools and sinks along the darker edges. Each one spans hundreds to more than 1,000 kilometers across, and thousands of them cover the visible face at any moment. That granulation pattern is not just an interesting texture. It is the visible sign of energy moving out from deep inside the star. Hot material rises because it is less dense, reaches the surface, dumps some of its heat as light, and then sinks again. This restless overturning stirs the outer layers of the sun the way boiling water stirs a kettle. As it does, it drags magnetic field lines along, stretching and twisting them in 3 dimensions. The sun's magnetic field is not a single simple bar magnet running from one pole to the other. It is a tangled, constantly changing structure generated by the motion of electrically conducting plasma in the interior. This solar dynamo is what turns slow internal flows into powerful magnetic fields that thread through the entire atmosphere. Where those fields become especially concentrated and push back against the rising plasma, something dramatic appears on the photosphere. You have probably seen pictures of sunspots, those dark patches that occasionally pepper the sun's face. They look small in a full disk image, but each one can be larger than Earth. They appear dark only by contrast, because they are cooler than their surroundings, though still thousands of degrees hot. Strong magnetic fields in a sunspot act like rigid bars, blocking the upward flow of hot plasma. With less fresh heat arriving, the region cools and dims relative to the brighter photosphere around it. Sunspots rarely appear alone. They tend to cluster in active regions, often arranged in pairs or groups where lines of magnetic force emerge from the surface in one spot and dive back in somewhere nearby. Between those footpoints, loops of plasma rise into the atmosphere, tracing out the invisible field. In ultraviolet and extreme ultraviolet images, these loops glow as arches of light, towering thousands of kilometers above the surface. They sway, expand, and sometimes snap in events that can release more energy in minutes than humanity uses in years. If you trace those loops outward, you often find them connecting into larger structures in the corona. Some loops rise high and then fall back, forming closed magnetic cages that trap hot plasma. Others stretch farther and open into the solar wind, forming coronal holes where material can escape more easily into space. The sun's outer atmosphere becomes a maze of pathways along which charged particles move, guided more by magnetic fields than by gravity. Sometimes plasma follows those fields in spectacular ways. A prominence can rise from the surface as a gigantic looping structure, a glowing arch of relatively cool, dense material held aloft in a magnetic hammock. Seen against a bright disk, that same structure appears as a dark filament, like a thread stretched across the sun. These prominences can hang in the corona for days or weeks, slowly changing shape, twisting and writhing as the underlying field evolves. If a prominence becomes too twisted or loses its magnetic support, it can erupt. When that happens, part of the structure collapses back onto the sun, while another part can be flung outward into space. In many cases, these eruptions are part of something even larger and more violent, a coronal mass ejection. In a coronal mass ejection, billions of tons of solar plasma can be hurled into space in a single event, riding on a bubble of distorted magnetic field that expands as it travels. It is tempting to imagine the sun simply flinging material off like sparks from a bonfire, but the mechanism is subtler. The key idea is magnetic reconnection. Magnetic field lines in a plasma do not like to cross each other. When they are forced together and pushed into sharp bends, they can suddenly change their configuration. In a reconnection event, field lines break and rejoin in a new pattern, releasing stored magnetic energy and converting it into heat, light, and motion. If you want a more familiar picture, think of twisting a rubber band between your fingers. As you wind it tighter, you can feel the tension build. At some point it becomes so tangled and stressed that it snaps free, unwinding in a blur and releasing all that stored energy in one quick burst. On the sun, the rubber bands are loops of magnetic field embedded in hot plasma. When they reconnect, the release can drive a solar flare. A solar flare is a sudden brightening in an active region, visible across much of the electromagnetic spectrum. In X-ray and ultraviolet images, a flare looks like a flash of brilliance, sometimes followed by spreading waves across the surface. It can last minutes to hours. The energy released accelerates particles to near light speed, heats plasma to tens of millions of degrees, and sends bursts of radiation streaming out into space. Many flares are minor flickers, but the largest ones rank among the most energetic events in the solar system. Flares often go hand in hand with coronal mass ejections, though the relationship is complex. Not every flare has a mass ejection, and not every mass ejection has a strong flare, but when they do occur together, the result can be a powerful space weather event. The flare delivers a pulse of radiation and energetic particles, arriving at Earth in minutes to hours. The mass ejection, moving more slowly, takes 1 to 3 days to cross the distance and slam into our magnetic field. We will come back to what that means for satellites and power grids later. For now, it is enough to hold one picture in mind. Imagine Earth's protective bubble of magnetism, the magnetosphere, as a kind of invisible comet shape around our planet, with a compressed side facing the sun and a long tail stretching away. A coronal mass ejection is like a giant gust of magnetized wind. When it arrives, it can squeeze and shake that bubble, inject energy into it, and trigger storms of charged particles that funnel down near the poles. Inside the corona, the violence of these events is accompanied by waves and shock fronts that ripple across the surface. Instruments have observed broad, expanding fronts that sweep over large parts of the sun after major eruptions. They are sometimes called EIT waves, named after an early instrument that saw them. Physically, they are waves in the plasma and magnetic field, similar in spirit to ocean waves racing out from a disturbance, but moving through an electrically charged gas instead of water. All of this drama unfolds on top of the quieter background structures we already talked about. Coronal holes, those darker regions with open field lines, feed steady, high-speed streams of solar wind that blow outward all the time. Where faster streams overtake slower ones, they can form co-rotating interaction regions, long-lived structures that spiral through the solar system like rotating arms of compressed plasma. These too can buffet Earth's magnetosphere when they sweep past. When you put all these pieces together, the Sun starts to look less like a single object and more like a layered system. At the bottom is the core, where fusion burns. Above that lie the radiative and convective zones, transporting energy outward. Then come the photosphere, chromosphere, transition region, and corona, each with its own typical temperatures, densities, and structures. Across all of them, magnetic fields thread and reconnect, coupling the layers and powering storms that reach far into space. From our hillside, that complexity is invisible. The photosphere hides the deeper layers, and the corona is too faint to see in daylight. Only during a total eclipse do most people ever glimpse the outer atmosphere at all. Even then, the experience is fleeting. The moon covers the sun for only a few minutes before the bright photosphere returns, washing out the delicate streamers with its glare. Without dedicated instruments, the true anatomy of the sun remains hidden. This is why solar observatories matter so much. The Solar Dynamics Observatory stares at the sun around the clock from space, taking images in multiple wavelengths every few seconds. Other missions, such as the Solar and Heliospheric Observatory and the twin Solar Terrestrial Relations Observatory spacecraft, watch from different angles and with coronagraphs that artificially block the bright disk, revealing the faint corona. Together, they let us watch prominences rise, loops form, and ejections launch in real time. When you watch a time-lapse of these data, the sun stops feeling like a static background and starts to feel like a weather system. Loops grow and shrink, active regions rotate into view and then disappear over the limb, flares flash and fade. Even the apparent calm periods are filled with motion on smaller scales, with spicules, small brightenings, and nanoflares constantly stirring the atmosphere. It is like watching satellite imagery of a planet where every cloud is made of fire. Soft questions naturally arise. How often does the sun throw a storm big enough to matter to us? Are we living through an unusual quiet period, or is this just normal behaviour? How much warning will we get before the next truly large event aimed at Earth? These questions are not just academic. They are the kind of questions that decide whether a satellite operator can move a craft to a safer mode in time, or whether a power grid operator can prepare for unusual currents flowing through long lines. If you zoom in even further, to scales below what most observatories can currently resolve, a new world of phenomena appears in models and in the latest high-resolution images. Tiny loop brightenings, sometimes called campfires, dot the lower corona in close-up views. They seem to be small bursts of heating, possibly connected to the long-standing puzzle of why the corona is so hot. In some simulations, countless small reconnection events inject heat into the plasma, like a storm of miniature flares too small to see individually. The idea that many tiny events could collectively heat the corona is one of the leading explanations for its extreme temperature. It is as if you warmed a room not with one large heater, but with millions of match heads striking and burning out every second. Each one is insignificant on its own. Together, they create a steady, warm bath of energy. Whether this picture is complete is still an open question, but it shows how much of the sun's life happens on scales we are only now beginning to access. As we keep pushing for sharper images and better models, we also keep uncovering deeper links between different layers. Waves seen in the chromosphere can propagate into the corona, carrying energy upward. Motion in the convective zone sets up global flows and cycles that modulate sunspot numbers over decades. The sun is not just layered in space, it is layered in time, with patterns that play out over minutes, hours, years, centuries, and longer. Some of those long-term patterns show up in the number and size of sunspots. Records going back hundreds of years reveal cycles in their abundance, with peaks and troughs repeating roughly every 11 years. These changes in sunspots track changes in magnetic activity more broadly. More sunspots usually mean more active regions, more flares, and more mass ejections. Fewer sunspots mean a quieter, less eruptive sun. Understanding this cycle is key to predicting when the star is likely to be most dangerous for our technology. You can think of the solar cycle as a kind of heartbeat superimposed on the constant background motion. During a maximum, active regions swarm across the surface, and images of the corona show tangled loops and bright patches everywhere. During a minimum, the disk looks cleaner, with fewer spots, and the corona often has simpler structures, with large coronal holes near the poles. The engine behind this cycle lies in the way internal flows twist and flip the global magnetic field, reversing its polarity roughly every 11 years. We will explore that deeper rhythm soon. For now, it is enough to recognise that the storms we have been talking about are not random. They ride on top of larger patterns that control when the sun is more likely to launch dangerous outbursts and when it tends to rest. This layering of small-scale storms on long-term cycles turns our nearest star into a system that is at once predictable and chaotic. Standing again on that hillside at sunrise, it is easy to feel far removed from all of this. Yet every beam of light and every gust of solar wind that reaches Earth has passed through this maze of loops, waves and eruptions. The delicate colours of dawn are the final, softened echo of a violent interior and an even more violent atmosphere. To fully understand what we are seeing, we need to go still deeper, into the heart of the star itself, where gravity and fusion first struck their uneasy truce. If we keep going deeper, we eventually reach a place where the sun stops looking like a sky object and starts looking like a story with a beginning. Our star did not switch on in an empty universe for our convenience. It was born inside a cold, dark cloud of gas and dust, in a region of space that might have looked almost empty to human eyes. To see its origin, we have to rewind the clock billions of years and follow gravity into the dark. Picture a giant molecular cloud spread across light years, with pockets of hydrogen, helium, and traces of heavier elements left behind by earlier generations of stars. The gas is cold enough for molecules to form, and the dust grains floating in it act like tiny shields, blocking starlight and letting the interior stay even cooler. From far away, this cloud might appear as a dark lane cutting across the bright band of the Milky Way, a place where light seems to go missing. Inside such a cloud, gravity and pressure are in a constant tug of war. The gas wants to collapse under its own weight, but its internal heat pushes outward. If a piece of the cloud is large and dense enough, gravity can win. Small random ripples in density or a passing shockwave from a nearby supernova can tip the balance. Regions that are just slightly denser than average start to pull in more material, becoming denser still in a runaway process. This is where the quiet cloud begins to break into fragments. Each fragment can become the seed of a new star. As gas falls inward, it speeds up, converting gravitational energy into heat. It also starts to spin faster, because the initial slight rotation of the cloud core is conserved as it shrinks. The same principle makes a figure skater spin faster when pulling their arms in. What begins as a slow swirl on light-year scales turns into a rapid spin as the collapsing region becomes compact. Near the center of that collapse, a dense object forms, wrapped in layers of gas and dust. This is the protostar phase. The forming star is still gathering mass from its surroundings, still buried in the remains of the cloud. Material that cannot fall straight in because of its angular momentum settles into a flat, rotating disk around the central object. That disk is more than a byproduct. It will eventually become the nursery for planets, moons, asteroids, and comets. Radiation from the growing protostar can be trapped by the surrounding dust, so much of the early story is invisible in ordinary light. Instead, astronomers observe young star-forming regions in infrared and radio wavelengths. There they see glowing cocoons, jets spraying out along the rotation axis, and disks silhouetted against the background. Each of these newborn stars is going through a version of the process that once built our Sun. We cannot see our own star's childhood directly, but we can study its siblings. In that rotating disk, dust grains collide and stick together, first forming clumps, then pebbles, then boulders. Over time, some of these bodies grow into planetary embryos, sweeping up material as they orbit. The disk becomes a busy place, with swirling rings, gaps where forming planets clear paths, and spiral waves stirred up by their gravity. While all of that unfolds in the disk, the real transformation that will define a star happens deep in the contracting core. As gas piles onto the protostar, the core becomes hotter and denser. The weight of the outer layers squeezes the interior, raising the temperature until the particles inside move at enormous speeds. At some point, the conditions become extreme enough that nuclear fusion can begin. The key players in this process are protons, the positively charged particles in the nuclei of hydrogen atoms. They naturally repel each other because like charges push apart. To fuse, two protons have to get close enough for the strong nuclear force to take over and bind them together. In a classical picture, they would need outrageous temperatures to smash through the electrostatic barrier between them. The Sun's core is hot, in the range of tens of millions of degrees, but not nearly hot enough for that barrier to be overcome purely by brute force collisions. If the universe followed only classical rules, the Sun would not shine the way it does. Quantum mechanics offers a different route. Instead of thinking of protons as tiny billiard balls with exact locations and paths, it treats them as wave-like objects with probabilities of being in many places. There is a small but real chance that a proton can slip through the energy barrier without having enough energy to climb over it. This is quantum tunneling. It is as if two people on opposite sides of a wall could occasionally find themselves together, not because they smashed the wall down, but because the rules of reality sometimes let them exist on the same side. In the core of the Sun, temperatures and densities are just right for enough protons to tunnel through the barrier and fuse. The main route is called the proton-proton chain. In simple terms, two protons come together. One transforms into a neutron while emitting a neutrino and a positron, and the result is a deuterium nucleus, one proton plus one neutron. More protons and neutrons join in, step by step, until helium nuclei form. Each time this sequence runs to completion, a small amount of mass is converted into energy. The famous equation that connects mass and energy tells us how much energy is released, but we do not need the equation to grasp the consequence. A tiny mass difference, on the order you might dismiss as rounding error, turns into a large burst of energy when multiplied by the factor that links mass and energy. In the Sun, these individual events happen in unimaginable numbers. Every second, a huge quantity of hydrogen is fused into helium in the core, and a fraction of the mass of that hydrogen is turned into energy. In more massive stars, another sequence called the carbon-nitrogen-oxygen cycle plays a bigger role, using heavier nuclei as catalysts to speed up fusion. In the Sun, this cycle contributes less, but it still hints at a bigger story. The elements carbon, nitrogen, and oxygen had to be created in earlier generations of stars and recycled into the cloud that formed our solar system. That means the Sun's very ability to shine the way it does depends on prior stellar generations. Our star is part of a cosmic family tree, not an isolated case. The energy produced in fusion appears first as high-energy photons and as kinetic energy of particles. The core becomes a seething plasma, where particles collide at high speeds and photons ricochet from one charged particle to another. The density is so high that a photon cannot travel far before being absorbed and re-emitted. The pressure created by this energy pushes outward, fighting the inward pull of gravity. When the outward pressure from fusion balances the inward pull from the star's own gravity, the collapse slows and stops. The protostar has become a main sequence star. In this stable state, the star burns hydrogen in its core at a rate set by its mass and internal conditions. For the Sun, this period of relative stability lasts for billions of years. During that time, its luminosity, the total energy it radiates, changes only slowly. This balance is delicate but self-regulating. Imagine the core of the Sun heating up slightly and the fusion rate increasing. That extra energy increases the pressure, which causes the outer layers to expand a little. Expansion lowers the core temperature and density, which slows fusion back down. If the core cools and fusion slows, gravity can pull the star inward a bit, compressing and heating the core, which boosts fusion. The Sun behaves like a system that resists big departures from equilibrium, even though tiny long-term changes still creep in. Those long-term changes matter. As the sun ages, helium ash from fusion accumulates in the core. The core slowly contracts under its own gravity, which raises its temperature and keeps fusion going in a surrounding shell. This process causes the sun's luminosity to increase over time. Early in Earth's history, the sun was dimmer. This creates a puzzle known as the faint young sun problem. Geological evidence suggests liquid water existed on the early Earth, yet a dimmer sun should have left the planet frozen solid. Possible solutions involve stronger greenhouse gases in the early atmosphere or different cloud patterns that trapped more heat. Whatever the exact combination, the key idea is that Earth's climate has had to respond to a star whose output has not been fixed. Even small changes in solar brightness over billions of years can make the difference between a world that stays habitable and one that does not. Our comfortable present sits on top of a long and fragile history of balance between a changing star and a changing planet. As the sun continues on its main sequence path, the timescales involved dwarf human history. If you compress the sun's roughly 10 billion year main sequence lifetime into a single day, humanity's entire existence so far would be just a blink near midnight. All of recorded history would be a fraction of a second. Yet for physics, even billions of years are finite. The hydrogen in the core is not infinite. When enough of it is converted into helium, the delicate balance we rely on will shift. Before we jump far into that future, it is worth pausing on the present. Right now, the sun is, in stellar terms, in its comfortable middle age. It has been shining steadily for over 4 billion years. Its output fluctuates a little with magnetic cycles and surface activity, but the core process of hydrogen fusion in the core continues calmly. The very predictability of this process is what allows life to persist on Earth. Plants can photosynthesize, oceans can stay liquid, complex ecosystems can adapt. If you step outside on a clear day and feel the sun on your skin, you are feeling the result of nuclear events that began deep in the core long ago. The warmth on your face is part of the outward flow of energy that started when protons tunneled through their repulsion and fused. The atoms in your body tell the same story from a different angle. Many of the heavier elements in your bones and blood were forged in stars and supernovae before the sun was born, then folded into the cloud that became our solar system. There is an often repeated line that we are made of star stuff. In the case of our sun, that phrase is not just poetic, it is traceable. The cloud that collapsed to form the sun and its planets was seeded with elements from earlier stellar deaths. Those elements entered the disk, entered the forming planets, and eventually entered the biology that evolved here. The sun is both a child of older stars and a parent to the worlds that orbit it. Of course, the sun is not just a friendly parent. The same fusion that supports its stable glow also powers the storms we see on its surface and in its corona. Magnetic fields generated by moving plasma in the interior feed into surface activity. The internal engine is not only a source of steady light, it is also the driver of cycles and storms that affect space weather, climate, and perhaps even subtle aspects of life. The link between the calm core and the restless surface is one of the puzzles we keep trying to solve. All of this raises a natural question. If the core is where the energy is generated, how does that energy actually reach the surface and beyond? What path does it take, and how long does that path really last? We know that photons born in the core do not take a straight line out. They wander, bounce, and change character. We know that other messengers, such as neutrinos, leave straight away, offering us direct information about fusion today. But the details of that journey and what it reveals about the sun's hidden interior deserve their own careful look. To follow the energy from the core to the surface, it helps to shrink down in your mind until you are not much bigger than a proton. Imagine you are created in a fusion reaction in the core, born as a high-energy gamma-ray photon in a place where matter is packed tighter than anything you have ever experienced. The temperature is in the tens of millions of degrees, the pressure is crushing, and you are surrounded by a swarm of particles that barely have room to move. There is no open sky, no clear path to the surface, only a dense fog of charged particles waiting to stop you almost as soon as you begin. You do not fly straight outward like a bullet through air. Instead, you travel a short distance before you run into an electron or a nucleus. The encounter does not look like a billiard ball collision. You are absorbed and re-emitted, scattered in a slightly different direction, with maybe a little less energy. Then you travel another short hop, collide again, and repeat. Over and over, you stagger through the core in a pattern that looks more like a drunk walk than a clean escape. This random walk is the single biggest reason why the light of the sun takes so long to reach us. Each step is tiny compared to the size of the star, and there are unimaginably many steps before you can reach the surface. On average, every time you move, you change direction. Sometimes you go a bit outward, sometimes you move sideways. Sometimes you even head back toward the center you just came from. Progress is real, but painfully slow. As you wander, something else is happening to you. You are losing energy. You start as a piercing gamma ray, far more energetic than the visible light that warms your face. Each interaction shares some of that energy with the plasma around you. By the time you reach the outer layers, if you make it that far, you have been downgraded. You become an X-ray, then ultraviolet light, and finally visible or infrared light. The core gives birth to high-energy photons, but the photons that actually escape into space are gentle by comparison. The region where this random walk dominates is called the radiative zone. There, energy moves primarily by radiation. Photons are absorbed and re-emitted, but the bulk of the material does not overturn on large scales. The density is still immense, but it gradually falls as you move outward from the core. The balance of forces shifts. Gravity still pulls inward. Pressure from the hot plasma still pushes outward. The temperature is dropping, but it is high enough that photons can still do most of the work of carrying energy. The timescale for a single photon to get from the core to the edge of the radiative zone is hard to picture. Some estimates suggest it can take hundreds of thousands of years on average. That means that the energy heating your skin today may have started as mass in the core when early humans were not yet walking upright. The sun is not a simple lamp that turns nuclear fuel into light in real time. It is a deep energy reservoir with a long delay between generation and release. At some point, you reach a layer where conditions change enough that radiation is no longer the easiest way to move energy. The plasma becomes more opaque to photons. Atoms come together into more complete structures. Photons do not travel as far between interactions. It becomes more efficient for hot gas to carry energy upward by physically moving than for photons to carry it by hopping. You have reached the base of the convective zone. In the convective zone, hot plasma rises from below, cools as it radiates energy, and then sinks back down. This motion sets up giant cells of circulation. You can picture it like a vast, three-dimensional version of boiling water on a stove. In a pot, heat from the burner warms water at the bottom. That water rises, cools near the surface, and sinks again. In the sun, the scales are much larger, and the cells are made of ionized gas instead of liquid, but the principle is similar. The boundary between the radiative zone and the convective zone is a region of particular interest called the tachocline. In this thin layer, the way the sun rotates changes sharply. The outer convective zone does not rotate like a solid body. Its equator spins faster than its poles. The inner radiative zone behaves more like a rigid object. Where these two regimes meet, there is strong shear, meaning layers sliding past each other at different speeds. This shear is thought to be a key part of the dynamo that generates the sun's magnetic field. You can think of the tachocline as a kind of gearbox for the star. Flows from the deep interior couple to flows in the outer layers, twisting and amplifying magnetic fields. Those fields then thread up through the convective zone and emerge at the surface as sunspots and active regions. Energy that began as fusion in the core becomes not only light, but also magnetic structure. The same photons that wander outward are sharing the star with fields that will later drive storms. Once you reach the convective zone, the nature of motion around you changes. Instead of a smooth gradient of density and temperature, you are carried along with upflows and downflows. Hot plasma rises in broad, slower columns. Cooler plasma sinks in narrower, faster plumes. Near the surface, these flows break into smaller granules, the cellular pattern we see in high-resolution pictures of the photosphere. You are no longer a lonely traveller bouncing through a crowd. You are a passenger inside a constantly overturning medium. At the very top of the convective zone, the plasma becomes transparent enough that photons can finally travel freely into space. This is the photosphere, the layer that defines the visible surface. When you emerge at this boundary, your last scattering sends you on a mostly straight-line flight out into the solar system. 8 minutes later, if you are aimed just right, you might hit the atmosphere of Earth and contribute to a sunrise or a bright afternoon sky. One of the strange consequences of this layered journey is that the light we see from the sun carries only indirect information about its interior. We can measure the spectrum and infer the temperature and composition of the photosphere. We can watch surface features evolve and track magnetism at the topmost layer, but the core, where fusion actually happens, is hidden behind hundreds of thousands of kilometers of dense plasma. We cannot send a probe there in any straightforward way. Instead, we listen to the sun. The star rings with waves that travel through its interior, much like sound waves travel through a bell or through Earth. These waves cause the surface to oscillate slightly, rising and falling in patterns that can be measured with sensitive instruments. This field of study is called helioseismology, the solar counterpart of the seismology that uses earthquakes to probe Earth's interior. By analysing the frequencies and modes of these waves, scientists can infer the temperature, density, and motion in different layers inside the sun. Imagine watching the surface of the sun and seeing it move up and down by small amounts in a complex pattern. Each point is shifting in response to waves that are bouncing around inside the star. Some waves travel radially, going inward and outward. Others travel along curved paths inside, trapped by the way density changes with depth. Together they form a rich spectrum, like the harmonics of a musical instrument, but with many more notes than you can hear with human ears. By matching observed frequencies to models, helioseismologists map out how fast the sun rotates at different depths and latitudes. They find that the outer layers have differential rotation, with the equator spinning faster than the poles. Deeper down, in the radiative zone, the rotation is more uniform. They also learn about the precise location of the boundary between these zones, and about subtle flows that move material north and south, as well as up and down. The sun, which once seemed unreachable, reveals its interior structure through these waves. While we are listening, another type of messenger is slipping straight out from the core. Every time fusion converts hydrogen into helium, it creates neutrinos. These nearly massless particles interact so weakly with matter that they can pass through entire planets without noticing. In the dense core of the sun, where photons are trapped by frequent interactions, neutrinos hardly slow down at all. They leave the core in seconds and stream straight out into space. If you could see neutrinos, the sun would not look like a bright disk at all. It would look like a roaring sphere of ghostly light, shining not only in the direction of its surface, but in all directions from its core. Trillions of solar neutrinos pass through your body every second, right now. Even if you never think about them, they are like a silent rain of evidence, telling us what is happening in the core almost in real time. Detecting them is not easy. Because neutrinos interact so rarely, you need huge detectors filled with material and shielded from other sources of radiation. Some famous experiments have used tanks of water or heavy water buried deep underground where cosmic rays are greatly reduced. Occasionally, a neutrino will interact with a molecule in that tank, producing a flash of light or some other signature that can be recorded. By counting these rare interactions, scientists can estimate how many neutrinos from the sun are passing through. For a long time, there was a puzzle. Experiments detected fewer solar neutrinos than theoretical models predicted. This was known as the solar neutrino problem. At first, people wondered if the models of the sun were wrong. If fusion in the core was slower than expected, the neutrino rate would drop. That would mean the sun was not what we thought it was. Yet the same models successfully explained the sun's luminosity and many other observations. The solution turned out to be even more interesting. Neutrinos, it seems, can change their type as they travel. Early experiments were only sensitive to one kind. Later detectors, with different techniques, found evidence for the missing types. When all were counted, the total matched the predictions. Instead of exposing a problem with solar physics, neutrino measurements confirmed our understanding of fusion in the core and revealed a new aspect of particle behavior. With photons, waves, and neutrinos together, our picture of the sun's interior becomes far less mysterious than it once was. We understand that energy is generated in the core by fusion, diffuses outward through the radiative zone, then is carried by convection in the outer layers before escaping at the surface. We can measure the internal rotation profile, map the location of the tachocline, and connect internal flows to surface magnetic patterns. We can check that fusion really is happening at the expected rate right now. All of this understanding, however, exists beside a very human perception. To your senses, the sun still looks like a bright circle, rising and setting predictably. The delay between energy generation and energy release smooths out many small fluctuations. The random walk blurs short-term changes. The star behaves, from our point of view, like a fairly steady source of light and warmth. Only when magnetic fields and surface activity come into play do we notice dramatic short-term variations. This raises an intriguing tension. The same star that is internally buffered and self-regulating can still produce flares and storms that matter to our daily life. The core is calm on human timescales. The atmosphere is not. In between lies the region where rotation, convection, and magnetism interact to create cycles of activity. To understand how a star that takes hundreds of thousands of years to deliver a photon can still flare dramatically in minutes, we need to look at those cycles more closely. As we turn from the deep interior to the patterns that play out on the surface and above it, a new picture of the sun begins to emerge. The steady engine in the core sets the baseline, but the outer layers turn that baseline into a complex rhythm. Sunspots come and go in repeating cycles. Magnetic fields flip polarity. The frequency of flares and mass ejections rises and falls. These patterns define the solar clock that our technology, and perhaps even our biology, quietly follow. When scientists first plotted the number of sunspots over time, that quiet clock began to speak. The dots on the graph did not spread out randomly. They rose and fell in a pattern, like a tide climbing and retreating again and again. Suddenly it was clear that the restless surface of our star had its own rhythm, and that rhythm might matter more than we once imagined. The first careful counts in the 1800s showed that sunspots go through a roughly 11-year cycle. Numbers climb from a low point, reach a peak where the surface swarms with dark spots, then fall again toward a minimum. The pattern repeats, with some cycles stronger and some weaker, but the basic pulse endures. It is as if the sun has a heartbeat, slow by human standards, but steady enough to build a calendar on. If you look not just at how many spots appear, but where they appear on the surface, another pattern emerges. At the start of a cycle, sunspots tend to show up at mid-latitudes in both hemispheres. As the cycle progresses, new spots form closer and closer to the equator. Plot their positions over time, and you get a shape that looks like wings of a butterfly. This butterfly diagram shows that the magnetic activity of the sun migrates, not just turns on and off. The 11-year cycle is only half of the deeper story. The sun's large-scale magnetic field flips polarity roughly every 11 years as well. That means it takes about 22 years for the magnetic field to return to the same orientation. This longer pattern is known as the magnetic cycle. Sunspots and flares ride on top of it, like waves on a slowly turning sea. During solar maximum, when the cycle peaks, the sun bristles with active regions. In visible light, sunspots dot the surface. In ultraviolet images, the corona glows with bright loops and hot knots everywhere you look. Flares and coronal mass ejections are more frequent and more powerful. The solar wind becomes more complex, with high-speed streams and slow flows interacting to create a choppy space environment. During solar minimum, by contrast, the sun can go weeks with hardly any spots at all. The corona often looks simpler, with large coronal holes near the poles and fewer active regions around the equator. Space weather tends to be quieter, yet even in these calm times, the solar wind continues to blow and small events still occur. The clock never truly stops, it only ticks more softly. There have been times when the cycle itself seemed to weaken for decades. Between the middle of the 1600s and early 1700s, sunspot counts plunged for a long stretch now called the Maunder minimum. During that period, very few spots were recorded, and some evidence suggests that the sun's overall activity was lower than usual. The Earth, at roughly the same time, went through cooler phases, often grouped under the label Little Ice Age. It is tempting to draw a simple straight line between low solar activity and cold climate. Reality appears to be more tangled. Volcanic eruptions, changes in ocean circulation, and other factors also played roles in those centuries. Still, the coincidence between a weak solar cycle and cooler conditions on Earth keeps drawing attention. It suggests that the solar clock can, on long timescales, nudge climate, even if it is not the primary control knob. On shorter timescales, we see the sun's influence through storms rather than slow drifts. Historical records tell of mysterious nights when the sky over places far from the poles lit up with moving curtains of red and green light. Long before anyone knew what the solar wind was, people watched auroras over Europe, Asia, and even the tropics during strong events. They wrote of ghostly fires in the sky, of silent battles of light, of omens and wonders. One of the most famous storms struck in the year 1859. A powerful solar flare and associated coronal mass ejection blasted out from the sun and reached Earth. Telegraph systems, the cutting-edge communication technology of that era, went haywire. Some operators reported sparks leaping from their equipment. In some cases, they could send messages even after disconnecting their batteries, because changing currents induced by the storm powered the lines. That event, often called the Carrington storm, is our vivid reminder of what a really strong solar outburst can do. In a world lit by candles and driven by steam, it mostly produced auroras and telegraph trouble. In our world, threaded with satellites, long power lines and digital systems, a similar storm would have far more targets to hit. When we study the solar cycle now, we are not just satisfying curiosity. We are checking the schedule of a force that can reach into our infrastructure. At the heart of space weather is the solar wind, the continuous outflow of charged particles from the sun. Embedded in that wind is the sun's magnetic field, stretched and carried outward. When a coronal mass ejection ploughs through the solar wind, it creates a moving bubble of denser plasma and stronger magnetic field. If that bubble crosses Earth's orbit and its magnetic field happens to be aligned in a way that can connect with Earth's field, energy can pour into our magnetosphere. Earth's magnetic field normally deflects most charged particles, guiding them around the planet. During a strong solar storm, the outer boundary of that field can be pushed inward. Streams of particles become trapped, forming and energizing radiation belts. Some then spiral down near the poles along field lines, slamming into atoms and molecules high in the atmosphere. As they collide, they transfer energy, which is re-emitted as light. This is the origin of the auroras. From the ground, an aurora can be one of the most beautiful sights you will ever see. Curtains of green, with fringes of red and purple, ripple and twist across the sky. Arcs appear, break apart and reform. Tall rays seem to reach down to you and then fade again. If you are lucky enough to stand under a strong display, you feel both very small and strangely connected to something far larger than yourself. You are watching a magnetic storm, millions of kilometers away, leave fingerprints in your night sky. But the same electric currents that light up the upper atmosphere can also cause trouble. As they flow and change, they induce currents in long conductors on the ground. Power lines, pipelines, and communication cables can pick up unwanted electrical surges. Transformers in power grids, designed to handle specific ranges of currents, can be stressed and in extreme cases damaged. In 1989, a strong solar storm contributed to a power blackout in Quebec that left millions without electricity for hours. High above Earth, satellites face their own set of risks. Charged particles can build up on their surfaces and then discharge suddenly, damaging electronics. Radiation can upset memory and computer systems, flipping bits and causing errors that must be corrected. Increased ultraviolet light during active times can heat and expand the upper atmosphere, increasing drag on low-orbit satellites. Without adjustments, their orbits can decay faster than expected, shortening their useful lives. Signals passing through the ionosphere, the charged layer of Earth's upper atmosphere, can also be disturbed. High-frequency radio waves that normally bounce off the ionosphere and allow long-distance communication can be absorbed or scattered during storms. Navigation signals from global positioning systems can be delayed or distorted, reducing accuracy. For aircraft routes over polar regions, where communication already relies more heavily on these systems, space weather becomes a practical safety concern. Even people can be affected. Most of us on the ground are well shielded by the atmosphere and Earth's magnetic field, but astronauts outside that protection, and passengers and crew on high-latitude flights at high altitude, can receive increased doses of radiation during strong events. Space agencies and airlines monitor solar activity and sometimes reroute flights or adjust operations to reduce exposure when forecasts call for high levels. With so much at stake, forecasting space weather has become a serious discipline. Observatories on Earth and in space track the sun's surface, its atmosphere, and the solar wind. Instruments sit at strategic points between Earth and Sun, sampling the wind before it reaches us. When they detect a shock front or a strong magnetic structure approaching, they can give us tens of minutes to a few hours of warning that conditions are about to change. Farther upstream, images of the Sun itself let forecasters spot active regions that might unleash flares or launch coronal mass ejections. When a big eruption is seen heading our way, models simulate how and when it will interact with Earth's magnetic field. These predictions are not perfect, but they are good enough to let satellite operators put spacecraft into safer modes and grid managers prepare for unusual currents. It is the space-age equivalent of watching the horizon for storm clouds. The solar cycle adds a slower beat on top of these day-to-day forecasts. During maximum, strong eruptions are more likely. During minimum, they are rarer but not impossible. Long-term planning for satellites, power grids, and even crewed missions beyond low Earth orbit now includes an awareness of where we are in the cycle. It is a quiet shift in mindset. We are beginning to treat the sun as a weather system, not just a background lamp. Of course, knowing that a storm is likely is not the same as knowing exactly when and how it will strike. Magnetic fields threading hot plasma evolve in 3 dimensions. Small changes in one region can cascade into larger events in ways that are challenging to model. Forecasts still carry uncertainty. Sometimes a dramatic flare fizzles into a minor impact. Sometimes a smaller-looking event turns out to be more disruptive than the images suggested. For you and me, the details of those models may not matter, but the consequences do. The device you use to watch videos, the navigation app that guides you, the financial systems that handle your transactions, and the grids that carry electricity into your home all depend on technologies vulnerable to space weather. At the moment, most of us think about storms only when we see lightning or heavy rain. In the future, we may check solar forecasts the way we check local weather now. It is worth pausing for a moment and imagining a day when a truly large solar storm hits modern Earth head-on. Auroras would probably be visible far from the poles, perhaps over dense urban areas that rarely see them. Some satellites might be knocked offline. Power grids could face serious stress. Communications could be patchy. For a while, many of the invisible systems we take for granted might blink, falter, or fail. It is not a guaranteed catastrophe, but it is a real risk. Thinking through that scenario is not meant to create fear. It is meant to make the sun feel real. This star is not just a symbol on classroom posters. It is an active partner in our daily lives. Its cycles and moods shape not only our climate and sky, but also the stability of our technology. When we invest in understanding the solar clock, we are quietly investing in the resilience of our civilization. All of this talk about hardware and infrastructure might make the story feel very mechanical, yet the sun's cycles could be touching much more than our power lines and satellites. There are hints, still debated and refined, that solar activity might subtly influence clouds, rainfall, and other aspects of the atmosphere. There are studies exploring possible links between solar cycles and biological rhythms, even mental health patterns, though these links are delicate and easy to misread. The idea that a cycle on the sun could reach all the way into our bodies and minds sounds dramatic. It risks sliding into superstition if we are not careful. But what if there is a narrow path between hard physics and that old human intuition that the sky matters? What if charged particles and magnetic fields, filtered through climate and biology, really do leave faint fingerprints on life? To find out, we have to follow the solar clock beyond circuits and into living systems. Life on Earth has always lived under a restless sky. Long before humans named the sun or mapped its cycles, plants were already stretching leaves toward its light, and animals were already timing their movements to dawn and dusk. Every heartbeat, every breath, happens inside an invisible bath of sunlight and charged particles. When you start from that simple fact, the idea that the sun might reach a little deeper into our bodies and minds stops feeling mystical and starts feeling like a question worth asking carefully. The most obvious connection is light itself. Photons from the sun drive photosynthesis in plants and algae, which in turn feed almost every food chain on the planet. They set the rhythms of day and night that every living thing must negotiate. Many organisms have internal clocks that sync to the daily light cycle, from flowers opening and closing to birds singing at first light. Even in humans, light hitting the eye resets the timing of hormones that control sleep, alertness, and mood. That daily rhythm is not the only one. Seasons arise because Earth is tilted, changing the angle and length of sunlight through the year. In temperate regions, plants bud and drop leaves in sync with those changes. In higher latitudes, animals migrate, hibernate, or grow thicker coats. The sun's path across the sky becomes the metronome for entire ecosystems. We have always known this part intuitively because we can feel winter and summer in our bones. But the 11-year solar cycle works on a different timescale. It is long compared to a day or a season, and short compared to the evolution of species. You do not wake up one morning feeling that the cycle has flipped. Yet the star does change slightly as the cycle turns. Its total brightness shifts by a small fraction. Not enough to explain modern climate change, but enough to be measured. Its ultraviolet output changes more, and its magnetic field and solar wind change a great deal. Those changes in the magnetic field and solar wind have a side effect. When the sun is more active, its stronger magnetic outflow provides better shielding against high-energy cosmic rays from outside the solar system. When the sun is quiet, more of those cosmic rays can reach the inner solar system and Earth. Cosmic rays are charged particles moving at very high speeds. When they strike the upper atmosphere, they trigger cascades of secondary particles and ionization. Some researchers have suggested that this extra ionization during quiet solar times might help seeds of cloud droplets form, especially low-level clouds that can reflect sunlight back into space. More clouds could mean slightly cooler global temperatures. In this picture, the solar cycle could modulate climate a little through cosmic rays and clouds. Experiments on Earth and observations of cloud cover and cosmic ray flux have found hints that support this idea and hints that contradict it. The effect, if it exists, is subtle and tangled with many other influences. What is clear is that the sun does affect the chemistry and structure of the upper atmosphere through both light and particles. Solar ultraviolet radiation shapes the production and destruction of ozone, particularly in the stratosphere. Solar proton events, bursts of high-energy particles during big flares, can temporarily change ozone concentrations near the poles. These changes can alter the temperature structure and winds high above us. Sometimes those disturbances ripple downward and slightly shift weather patterns nearer the surface. From the point of view of a forest or an ocean, these effects are small compared to the daily cycle of light and the seasonal tilt of Earth. Yet for delicate systems, even small nudges can matter. Phytoplankton near the ocean surface, for example, are sensitive to ultraviolet radiation. Shifts in ultraviolet output with the solar cycle might change their growth rates by a little, which could ripple up through food webs over time. The same is true for plants and microbes on land that rely on narrow bands of light for key processes. Then there is the magnetic environment itself. Many animals appear to sense Earth's magnetic field and use it for navigation. Migrating birds can follow magnetic lines over long distances, even at night or in cloudy weather. Sea turtles return to the beaches where they hatched, guided in part by magnetic cues. Salmon find their way back upriver, and some insects also appear to steer by magnetism. The exact sensing mechanisms are still being unravelled, but experiments show that changing magnetic fields can alter their orientation. When a strong solar storm arrives, it can disturb Earth's magnetic field, especially near the poles and in regions where auroras flare. For an animal that relies heavily on magnetic maps, a sudden distortion is like someone warping the compass. There are reports that some mass strandings of whales and dolphins coincided with severe magnetic disturbances, though many other factors can also cause strandings. Birds sometimes show unusual flight paths during storms. It is hard to prove cause and effect, but the timing keeps drawing attention. For humans, the daily and seasonal patterns of sunlight are direct and obvious. Exposure to morning light helps reset our internal clocks. Light in the blue part of the spectrum hitting special cells in the eye signals the brain to suppress melatonin, a hormone that makes us sleepy, and to boost other chemical signals linked to alertness. Many people notice that their mood dips during long dark winters far from the equator, a pattern often called seasonal affective disorder. Bright light therapy can help, which is a gentle reminder that our minds are not fully separate from the sky. The 11-year solar cycle adds another layer. Several studies have reported small correlations between periods of high solar activity or strong geomagnetic storms and changes in rates of heart attacks, strokes, or arrhythmias. Others have looked at hospital admissions, suicide rates, or mental health diagnoses around times of disturbed geomagnetic conditions. Some of these studies find patterns, others do not, or they find different patterns in different places. If you put all of this literature on a table, it does not point to a simple, clean story. The effect sizes, when they appear, are often tiny compared to the influence of known factors such as diet, pollution, or access to healthcare. The data can be noisy, and it is easy to mistake coincidence for cause. The safest statement today is that there might be small effects of solar and geomagnetic activity on human health, but they are subtle, and we do not yet fully understand the pathways. Scientists have proposed several possible mechanisms. One involves changes in the weak electric fields that exist in the atmosphere and at the surface during geomagnetic storms. Another involves possible effects on melatonin production and circadian rhythms, either through light changes or through magnetic influences on brain chemistry. There is also the simple fact that people behave differently during geomagnetic storms in some contexts. For example, more polar flights may be rerouted, and people in high latitudes may stay up longer to watch auroras, changing sleep patterns. Then there is the more dramatic idea that the phase of the solar cycle at the time of your birth could leave a faint imprint on your life. Some studies have compared large numbers of people born near solar maximum to those born near solar minimum and tracked outcomes such as lifespan or certain disease risks. A few of these analyses have reported small differences. One interpretation is that higher cosmic ray flux during solar minima might slightly increase mutation rates in germ cells or developing embryos, nudging the distribution of risks by a tiny amount. Even if that picture holds up under more scrutiny, the differences are small on an individual level. Lifestyle choices, social conditions, and random chance play far bigger roles in a single person's life than the solar cycle at birth. This is not destiny written in the sky. It is more like a gentle statistical breeze, one line among many in the story of a population. It sits in a very different category from astrology, which claims specific personality traits or fates based on birth time without grounding in physics. The temptation to slide from subtle statistics into cosmic storytelling is strong. Humans have always looked up and asked whether the sky is trying to tell them something. We named constellations, wrote myths about eclipses, and assigned meaning to planetary alignments. In that context, the idea that your life might be connected in some way to the solar cycle carries a real emotional pull. It feels like a bridge between ancient intuitions and modern science. That is exactly why caution is so important. There is a real, testable physical chain that connects the sun to Earth. Magnetic fields and particles modify the upper atmosphere, which can influence climate, which can influence ecosystems, which can influence human societies and bodies. But every link in that chain is complex and sometimes weak. If we care about truth, we have to resist the urge to make the chains simpler or stronger than the data support. At the same time, it would be a mistake to dismiss the sun's biological influence as limited to the obvious. Even the most conservative view accepts that sunlight shapes our sleep, mood, and health through circadian rhythms and vitamin D production. Extended darkness can harm us. Gentle exposure to natural light often helps. We evolved under a moving pattern of light and dark, not under the steady glow of artificial screens. Our brains and bodies still carry that heritage. There is also a quieter psychological effect. Simply knowing that the star above us is not a static ornament, but a dynamic, cycling engine, can change how you feel about your place in the world. The sunbeam on your desk is not just a convenience. It is the end result of nuclear fusion, photon diffusion, convection, and magnetic storms. It has passed through variations in the solar wind and through Earth's own shield before landing on your skin. Awareness of that chain can bring a sense of connection that no horoscope can match. Imagine for a moment that you could lay your own life out as a line next to a graph of solar activity. Birth, childhood, key decisions, moments of joy and loss, all marked along one axis. Peaks and troughs of sunspot numbers along the other. Your mind will instinctively look for patterns because that is what minds do. Perhaps you will spot coincidences that feel meaningful. The important question is not whether they feel meaningful, but whether they are more than what chance would produce in any random pairing of cycles. This is where science and humility meet. We can use careful statistics to test whether solar cycles leave real fingerprints on populations. We can design experiments to look for magnetic sensitivity in cells or organ systems. We can build better models of how changes in the upper atmosphere might trickle down into weather and climate. At every step, we must be ready to find that some connections are real and others are mirages. Meanwhile, the practical side of living under a restless star keeps pressing forward. Farmers and fishers still watch the seasons far more than the solar cycle. But satellite operators, grid managers, and aviation planners now watch solar indices almost as carefully as local weather. As our technology becomes more tightly linked and more delicate, the sun's moods become harder to ignore. The line between biology and infrastructure starts to blur. Human health depends both on our bodies and on the systems that support them. For astronauts and future explorers who venture beyond Earth's magnetic cocoon, the sun's influence becomes even more personal. Solar storms can deliver dangerous radiation doses outside strong shielding. The timing of missions, the design of spacecraft, and the health of crews will be shaped by the solar cycle in ways that go beyond statistics. For them, the question is not whether the sun nudges risk probabilities by a fraction. It is whether it throws a storm during a spacewalk. All of this adds up to a simple but profound shift in perspective. We are not living under a friendly lamp that we can treat as a constant. We are living inside the extended atmosphere of a star. Our planet is a small bubble inside a vast stream of particles and fields. Life has always been shaped by that environment, even if the details are only now coming into focus. The more we learn, the more it feels as if every heartbeat really does echo faintly with the rhythm of the sun. Still, there are limits to what we can infer from afar. Photons and neutrinos tell us about the core. Waves and surface motions reveal internal structure. Records of climate, biology, and health tease us with hints of deeper connections. But to truly understand how this star's activity is woven into the space around us, we have to go closer. We need to ride into the region where the solar wind is born, where the corona is heated, and where the seeds of storms that touch both satellites and cells are first sown. To do that, humanity has started sending metal shells with delicate instruments directly toward the fire, skimming through regions where the heat would destroy any unprotected object. Those probes are tasting the plasma, feeling the magnetic fields, and sending back data that challenge our assumptions. They are our first real attempt to walk into the furnace that feeds both our gentle dawns and our most dangerous space weather. What they are finding is changing our picture of the sun yet again, and it points toward a mystery that sits right at the edge of what we understand. When you send a fragile machine into that environment, you are not just doing engineering, you are making a statement about how badly you want answers. The sun is not kind to visitors. Any normal material would quickly heat, warp, and fail as it moves closer. Yet we have built craft that can survive long enough to take a sip from that fire and send the taste back across the void. One of the boldest of these explorers is the Parker Solar Probe. It follows an orbit that dives closer to the sun than any spacecraft before it, skimming through the outer corona. To get there, it uses repeated gravity assists from Venus, shaving away orbital energy step by step. Each pass bends its path inward and lowers its closest approach. Over time, its elliptical orbit grows more extreme, bringing it into regions once thought unreachable. Near its closest approach, the spacecraft races through space at hundreds of thousands of kilometers per hour. At that speed, it could circle Earth in a few minutes, yet the sun still fills much of the sky from its point of view. The heat shield on the front of the craft glows white hot, blocking intense radiation from reaching the instruments tucked in its shadow. Behind that shield, sensors taste the plasma, count particles, and measure fields. The data they return do not look like photographs. They are streams of numbers, describing how fast particles move, how dense the plasma is, and how the magnetic field lines twist and turn. When scientists convert some of those measurements into sound, speeding up the fluctuations until they reach our hearing range, you can literally listen to the sun. The solar wind becomes a rushing hiss, rising and falling. Magnetic waves become eerie whistles and chirps. It feels like eavesdropping on a storm that never ends. Another mission, the Solar Orbiter, takes a different path. It travels in an orbit that gradually tilts out of the plane of the planets. Over time, this allows it to look down on the sun from higher latitudes and eventually to glimpse the polar regions more clearly. Those poles are crucial to understanding how the global magnetic field flips and how the solar cycle truly works. Yet they are hard to see from Earth or from spacecraft that stay in the ecliptic. Solar Orbiter carries high-resolution images that have revealed tiny, bright features scattered across the lower corona. These little flashes, often called campfires, are too small to notice in traditional full-disk views. Up close, they look like miniature flares dotted everywhere, each lasting only a short time. Their existence supports the idea that countless tiny reconnection events might be helping to heat the corona from below. Parker Solar Probe has also revealed surprises closer in. It has flown through regions where the solar wind has not yet fully settled into the smooth flow we see near Earth. In these regions, the magnetic field lines sometimes suddenly bend back on themselves, creating structures called switchbacks. These are abrupt reversals, like kinks in the flow, where the direction of the magnetic field flips for a moment before snapping back. They might carry clues about how energy moves from the lower corona into the outer wind. Both missions have also probed the dust near the sun. At certain distances, the intense radiation and plasma environment can vaporize dust grains, carving out a region with fewer particles than expected. This dust-free zone changes how sunlight scatters and how the solar wind evolves. It is a reminder that the space near the sun is not simply empty. It is a place where matter is constantly being reshaped by heat and radiation. These close-up measurements speak directly to one of the most stubborn puzzles in solar physics. The corona, the outer atmosphere we see during eclipses and in ultraviolet images, is vastly hotter than the visible surface below it. The photosphere, the layer we see, sits at a few thousand Kelvin. The corona can reach 1,000,000 Kelvin or more. Energy must be flowing upward somehow and being deposited in the thin outer gas. But how that heating happens in detail is still not fully pinned down. There are two main classes of ideas. One is that waves generated by convective motions and magnetic shaking in the lower layers travel upward and dump their energy in the corona. These could be Alfvén waves, a type of magnetohydrodynamic wave that travels along magnetic field lines through plasma. As they move into regions where conditions change, they might convert into other modes, steepen and dissipate, heating the surrounding gas. The other class centers on small reconnection events. In this picture, magnetic fields pushed together by convective flows are constantly reconnecting at tiny scales. Each reconnection event produces a small burst of heat, a nanoflare. On their own, nanoflares are too weak to notice, but if they are numerous enough, they can maintain the corona at its high temperature. The campfires seen by solar orbiter may be larger cousins of these events, visible hints of a much more crowded landscape of energy releases. Reality might use both mechanisms at once, along with others we have not yet fully understood. The corona is a complex stage where waves, turbulence, and magnetic reconnection all interact. Different regions may be dominated by different processes. Open field lines that lead into the solar wind might be heated mainly by waves. Closed loops above active regions might be heated more by reconnection. Parker and Solar Orbiter are giving us the first direct close looks at these interactions. Then there is the solar wind itself. As it streams away from the sun, it accelerates from subsonic to supersonic speeds. Something backs that acceleration, supplying energy and momentum to the plasma as it moves outward. Waves travelling along magnetic field lines could transfer their energy to particles, pushing them faster. Turbulence in the wind could cascade energy from large scales to small scales and eventually into heat. Reconnection in open field regions might catapult plasma outward in bursts that contribute to the flow. Parker has flown through the region where this transition is happening. It has measured changes in the distribution of particle speeds, seen signs of waves and turbulence, and documented how the magnetic field geometry evolves with distance. Each pass cuts a new slice through the environment at a slightly different distance and angle. Over time, those slices will add up to a three-dimensional picture of how the wind is born and shaped. All of this matters because the solar wind is not just a background breeze. It carries the sun's magnetic field with it, shaping the space around all the planets. It defines the size and shape of the heliosphere, the bubble that separates our local space from the interstellar medium beyond. It controls how cosmic rays enter the inner solar system. It sets the stage on which coronal mass ejections travel. To understand superstorms, we have to understand the quieter wind through which they move. When a large coronal mass ejection erupts, it ploughs through the existing solar wind like a wave through choppy water. Its magnetic field can interact with the background field in complex ways. Sometimes it reconnects with the ambient field and weakens. Sometimes it stays coherent and strong. The density and speed of the surrounding wind also matter. A fast ejection moving into a slower wind can drive a strong shock front, compressing and heating the plasma ahead of it. Probes scattered throughout the inner solar system occasionally find themselves inside these structures. They measure the sudden increase in particle density, the rotation of the magnetic field, and the drop in temperature behind the front. When multiple spacecraft line up, we can watch the same storm evolve as it travels, changing its shape and strength. These multi-point observations give us a better sense of how a storm launched at the Sun transforms into something that might later crash into Earth. We also dig through indirect clues from the past. Ice cores contain records of certain isotopes produced when cosmic rays and solar energetic particles hit the atmosphere. Tree rings preserve hints of conditions centuries ago. In those records, scientists have found evidence for solar events even stronger than the Carrington storm. Events that produced unusual spikes in isotopes. These do not have direct technological impacts to measure because they happened before modern systems existed, but they suggest the Sun is capable of throwing even larger tantrums than we have witnessed in the satellite era. Models that combine what we know about the solar cycle, magnetic field evolution, and historical data estimate how often storms of various strengths might occur. A Carrington-level event might be expected every century or two, an even stronger one, perhaps once every many centuries. These numbers are uncertain. The Sun does not keep a neat logbook for us, but they remind us that low probability does not mean impossible. It means rare enough that we often forget to plan. If such an event were aimed directly at Earth now, the results would not be limited to pretty auroras and confused telegraph operators. Power grids could see large induced currents over vast regions. Transformers, especially those not designed to handle strong geomagnetically induced currents, could be damaged in ways that take time and money to repair. Satellites might fail in clusters. Navigation and communication systems could be degraded for days. The economic costs could be enormous, and recovery would not be instant. This is why some people speak of solar superstorms in the same breath as earthquakes or pandemics. They are low-frequency, high-impact events. You cannot stop them at the source. You can only understand their statistics, harden your systems, and make plans for how to respond. In that sense, space weather prediction is not just a scientific curiosity, it is a form of risk management for a civilization built on long wires and fragile electronics. It is also why the data from Parker and Solar Orbiter carry such weight. The better we understand how energy moves from the convection zone into the corona, how the solar wind accelerates, and how magnetic fields store and release energy, the better we can model the conditions that lead to the biggest eruptions. We may never predict every flare or storm precisely, but we can improve our sense of which regions are more likely to erupt and how dangerous a given eruption may be when it leaves the sun. There is a strange poetic symmetry in all this work. We are a species that learned to make tiny, controlled versions of the sun's fire here on Earth, in reactors and weapons. We built technologies that depend on delicate control of electrons and fields. Then we discovered that the large, uncontrolled version of that fire in the sky can reach out and push on our systems from 93 million miles away. Now we are sending machines back toward the source, asking the star to teach us how it actually works. When you look at an image of the corona from one of these missions, you are seeing more than an aesthetic pattern. You are seeing a set of processes that have direct consequences for power in your home, for the navigation of aeroplanes, for the safety of astronauts, and for the long-term stability of the space environment. The wisps and loops are threads of a machine that we are only beginning to read. The question is, what we will do with that knowledge. Will we treat the sun as a hazard to be feared and endured, or as a partner whose moods we must learn and respect? Will we continue to build systems that ignore its cycles and storms, or will we design with its behavior in mind? And beyond the next flare or storm, what does this relationship mean for our distant future, as the star itself slowly changes and we start to think not just about surviving its tantrums, but about living with its aging heart? If you zoom out in time, the sun's cycles stop looking like the main story and start looking like ripples on a much bigger wave. The star we live with today is not the star that always was, and it is not the star that always will be. It has a biography, with a childhood in a dark cloud, a long middle age on the main sequence, and an old age still ahead. Right now, we happen to live during the long, stable middle chapter, when hydrogen fusion in the core is steady and the surface temperature and brightness are just right for liquid water on Earth. That chapter feels eternal to us. Yet in stellar terms, it is only one act in a larger play. As the sun quietly burns hydrogen into helium in its core, the balance of ingredients slowly changes. Helium ash accumulates, and the core contracts under its own weight. That contraction raises the core temperature and density, keeping fusion going in a surrounding shell, even as central hydrogen is depleted. The result is a slow, steady increase in the sun's luminosity over billions of years. Geological and climate models suggest that, long before the sun visibly swells, this brightening will make Earth less comfortable. At some point in the distant future, perhaps a billion years or so from now, feedbacks in our atmosphere and oceans could push the planet into a moist greenhouse state, where oceans begin to evaporate. Life, if it still exists then, will face a different sky. Farther ahead, when the core hydrogen is essentially gone, the changes accelerate. The sun's core, now mostly helium, contracts further and heats more. Hydrogen fusion continues in a shell around it, pumping out energy that inflates the outer layers. The star swells into a subgiant and then a red giant. Its surface cools and reddens, but its total luminosity climbs sharply. The photosphere drifts outward, engulfing the orbit of Mercury and likely Venus, and coming perilously close to, or even beyond, Earth's present orbit. Tidal interactions and mass loss complicate the details, but the inner solar system will be a very different place. In that swollen phase, the sun will lose a significant fraction of its mass through strong stellar winds. As mass drains away, the gravitational grip that holds the planets weakens. Their orbits will expand, like stones on a string suddenly attached to a lighter weight. Depending on the exact interplay of expansion and drag, Earth could be swallowed or survive as a scorched, airless world circling a bloated red star. Either outcome will not resemble the blue marble we know. Deep inside, the helium core will eventually reach conditions where helium itself can fuse into heavier elements, mainly carbon and oxygen. For stars like the Sun, this transition is dramatic. The core is so dense that when helium fusion finally ignites, it does so in a runaway burst, often called a helium flash. We would not see this from outside, as a catastrophic explosion, but inside, the core reorganizes quickly. Afterward, the Sun settles into another temporary balance, fusing helium in its core and hydrogen in a shell. It will be more compact than at its peak red giant size, but still much larger and more luminous than today. Later, when the helium fuel is exhausted, the star will wander through another giant phase, driving even stronger winds. Pulsations in the outer layers and complex interactions between shells of burning material will cause the Sun to shrug off its remaining envelope. The gas drifting outward will be lit from within by the hot, exposed core, forming a planetary nebula. Despite the name, this has nothing to do with planets. It is a glowing bubble of gas, a final display of colour and shape, expanding into space. At the centre of that nebula, the remnant core will cool and shrink into a white dwarf. This compact object will contain roughly half the Sun's original mass, packed into a volume comparable to Earth's. It will no longer have fusion in its core. Instead, it will glow with residual heat, slowly radiating away its stored energy over billions of years. The solar system, if any planets remain, will orbit this dense ember. Our familiar Sun will be gone, replaced by a faint white point of light surrounded by the relics of its earlier life. For us, all of this lies unimaginably far in the future. The timelines involved are so long that they can feel abstract, like myth rather than physics. Yet the inevitability of stellar evolution raises a question we cannot entirely dodge. If our star will eventually change in ways that make Earth uninhabitable, what kind of civilization do we want to be in the time we do have? Do we treat the Sun as a benevolent backdrop until it betrays us? Or do we learn to live with its nature, plan around its cycles, and think honestly about long-term stewardship of our own actions? Sometimes this question surfaces in surprisingly practical ways. One example that keeps popping up is the idea of sending our most dangerous waste into the Sun. On the surface, it sounds simple and elegant. Take long-lived radioactive waste, strap it to rockets, aim it at the star, and let the Sun's immense heat and gravity erase the problem forever. No more worrying about storage sites, geological timescales, or future generations accidentally digging into old repositories. The Sun, after all, has plenty of energy. What is a little extra mass to it? The trouble starts as soon as you look at this idea through the lens of orbital mechanics. Right now, Earth and everything on it, including your proposed waste containers, are orbiting the Sun at about 30 kilometers per second. That sideways motion is what keeps us in a nearly circular path instead of falling straight in. To send something into the Sun, you do not just point a rocket straight at it and fire. You have to get rid of almost all of that sideways speed so that gravity can pull the object down in a tight spiral. Cancelling 30 kilometers per second of orbital velocity is a huge task. Chemical rockets, the kind we actually use to launch things from Earth, do not have that kind of reserve speed on top of the energy needed to escape Earth's gravity well. Even if you think creatively and use gravity assists from other planets to reshuffle velocities, the mission becomes complex, expensive, and risky. In practice, it is often easier, in terms of required speed change, to fling an object out of the solar system entirely than to make it fall into the Sun. There is another layer to the problem. To even start this journey, you have to launch the waste into space. Launches fail. Rockets explode on the pad or in the lower atmosphere more often than we like to admit. When a normal payload is lost, the main costs are financial and reputational. If that payload is concentrated radioactive waste, a launch failure could scatter dangerous material over a large region. You have traded a slow, controllable risk in deep geological storage for a small but catastrophic risk at every launch. Even if you imagine a future with much more reliable launch systems and high-performance propulsion, the question remains whether using the Sun as a cosmic incinerator is wise. Our star may not care about a few extra tons of heavy nuclei. It has already forged and swallowed far more in its core, But the act of firing waste at the sun says something about how we see our place in this system. It treats the star as a bottomless trash can, a convenient sink for problems we do not want to carry. That attitude, scaled up, has not served us well on Earth. By contrast, storing nuclear waste safely in deep geological formations, recycling some of it with advanced reactor designs, and reducing its production in the first place, are solutions that involve learning to live within the constraints of our planet. They are harder and less dramatic than launching waste into the sky, but they rest on better physics and risk management. The same is true for other long-term challenges. We can choose quick, theatrical fixes that push problems outward, or we can do the slow work of understanding and responsibility. Thinking in orbits also forces us to face a less comfortable truth. We are not separate from the star. Our paths are already tied together by gravity and motion. Every kilogram of material we move into space stays within that shared system, unless we deliberately give it enough push to leave. Every satellite, every piece of debris, every probe becomes another actor in the dance between sun, planets, and fields. Flinging our worst leftovers toward the sun does not change that web of connection. It just hides the consequences inside a furnace we do not have to look at. If you step back from the technical details, a pattern starts to emerge. The sun is both a source of risk and a source of possibility. Its storms can damage our infrastructure, yet its flux of energy offers more power in an hour than humanity uses in a year. Its long-term brightening will eventually push Earth out of the comfortable zone, yet its stable middle age has given life time to flourish and intelligence time to arise. The way we respond to both the danger and the gift will say a lot about us. One path leads toward denial and short-term thinking. We build ever more complex systems that ignore solar cycles, treat space weather as a rare annoyance, and assume that future generations will somehow handle both the sun's minor tantrums and its major transformations. We push waste and risk out of sight, upward or outward, and hope that gravity and distance will make them go away. In that path, the sun remains a background light until something goes badly wrong. Another path is harder but more interesting. In this path, we accept that our civilization is embedded in a star's environment, not perched outside it. We design power grids and satellites that can ride out storms. We integrate solar forecasts into everyday planning. We use the sun's energy more directly and carefully, reducing our dependence on fuels that destabilize climate. We think about the slow changes in stellar output not as doom, but as boundary conditions for very long-term planning. It might even push us to seriously consider becoming a multi-planet species, not as an escapist fantasy, but as a rational response to living with a changing star. Colonies on Mars or moons in the outer solar system would face their own brutal challenges. They would not be safe havens in any simple sense, but spreading out changes the odds. It reduces the chance that a single event, whether solar, terrestrial, or self-inflicted, ends the entire story. All of this can feel distant when you are standing in your kitchen, watching sunlight fall across the floor. On an ordinary morning, with coffee in hand, the sun is just there. It rises, it sets, it warms the air and powers the weather and charges the solar panels on a few roofs. The scale of fusion, of corona, of orbital mechanics does not intrude. That is part of the paradox. Our star is both the most ordinary thing in the world and the most extraordinary. If you let yourself sit with that paradox for a moment, something shifts. The familiar glow through your window becomes a signal from a vast nuclear engine that has been running for billions of years. The gentle warmth on your skin traces back to protons tunneling in the core, to photons wandering through dense plasma, to magnetic storms in a halo of fire, to particles streaming through space and brushing Earth's magnetic shield. The fact that you can stand here at all, thinking about these things, is a consequence of that chain holding steady. We do not control the sun. We never will. What we can control, at least in part, is how well we understand it and how wisely we live under it. We can choose to treat each new probe, each new dataset, each new model as a way to deepen not only our knowledge, but also our sense of responsibility. We can be the kind of species that learns its star's language and adapts, instead of pretending that the sky is a static backdrop. The next time you see a sunrise or a sunset, you might find that it feels a little different. The colours will still be there, the calm, the quiet, but behind them, you might glimpse the turbulence of the corona, the hidden cycles in magnetic fields, the slow brightening over eons, and the distant future in which this gentle disk becomes a swollen red giant. You might think of the waste we decide to bury or launch, the grids we choose to harden or neglect, the missions we send to taste the solar wind. In that moment, the sun stops being just a symbol on a weather app and becomes what it truly is. A star, imperfect, evolving, dangerous, generous, and absolutely central to everything we are and might become. Living with it will always involve risk. Turning away from it will never be an option. Our task is to stand in that light with open eyes and decide what kind of story we want to write under its glow.